All right, for homework 17, we are looking at the alternating series test for the most part. So determine the convergence or divergence of the series. Because I see a negative 1 to a power, the first thing I want to make note of is that these terms are alternating. And if you're not sure, or if it's a weird expression other than n or n plus 1, you should plug numbers into it to double check, like if it's 2n plus 1 or something like that. But yeah, this is going to give me alternating 1 and negative 1. The next thing you want to show is that the terms are decreasing to 0. You take this limit in absolute value, so ignore the negative 1 to a power. That limit is 0. This is a bottom-heavy expression. And then finally, you want to show that the terms, again, in absolute value, are decreasing. So the n plus 1th term, which would be 1 over n plus 2, is less than the nth term. That's just saying the third term should be smaller than the second term if you have a decreasing series, which is true. So if I can state all three of these things, then I can say that this series converges by the alternating series test. All right, same thing on number 18. It's true that negative 1 to the n will make this alternating. The limit as n approaches infinity of 1 over ln n plus 1. This is bottom heavy again, so that limit is 0. And I want to show that it's decreasing, so I plug in n plus 1, I get ln of n plus 2. That would be smaller than 1 over ln of n plus 1, because a larger denominator gives you a smaller fraction overall. So all three of the requirements are true, so this converges by AST. For number 20, these terms are alternating. The limits as n approaches infinity of n over n squared plus 5. This is still bottom heavy, so that limit is 0. And if you plug in n plus 1, you would get n plus 1 on top over n plus 1 squared plus 5, and that's less than n over n squared plus 5. N versus n plus 1 in the numerator. I know n plus 1 is a bigger numerator, but the n plus 1 squared is going to grow faster than just the n squared in the denominator. So this is true. You're not really going to have to go through extra work to prove that that's true. So again, this one converges by alternating series test. If these are multiple choice problems, they're really nice because you don't necessarily have to write all of this out. Also, I would just want to make a note here. If the terms are approaching 0, then they are decreasing, right? Like these are positive terms in absolute value. And so, yeah, so we're talking about these two kind of go hand in hand. So anyway, if it's not free response, we'd be able just to kind of skip all this writing stuff. All right, take a look at 23. Alternating again, that's true. This time we have the limit as n approaches infinity of a linear expression over a natural log expression. Now, I can think about function races in my head. A linear function does grow faster than a natural log. Maybe the natural log grows faster for a little while, but eventually it does not grow as fast. But you can also do a round of L'Hopital's method. I'm not like formally doing it, but I would technically get infinity over infinity. In my head, it's like small infinity over big, but the derivative of n plus 1 would just become 1. The derivative of ln n plus 1 would be 1 over n plus 1. You can flip this around if you like, or you can just say this is like 1 over 0. Either way, you get infinity for that limit. So it's not that this diverges by alternating series test, because remember from our notes, it's called the alternating series test for convergence. So we really just violated the nth term test here. So this diverges by nth term test. Remember, function races are our informal way of deciding what a limit should be. if you're not sure, or if there's a more complicated expression in the natural log, instead of just like n+1, if there are exponents in there or something, then you would want to do L'Hopital's rule just to be sure. All right. Number 30, this one is alternating. It's true, -1 to the n. And the limit as n approaches infinity of 1 over 2n plus 1 factorial, that's definitely bottom heavy. So that's 0. And the last thing is to show that the terms would be decreasing. So when you plug n+1 into this, you would be getting 2n plus 2 plus 1. So 2n plus 3 factorial is less than 2n plus 1 factorial. So all three things are true. So this converges by alternating series test. And for 32, we have an alternating series again, -1 to the n plus 1. Now I'm going to do my limit as n approaches infinity of square root of n over cube root of n. Now again, technically that's infinity over infinity, but remember back in chapter 1, we learned about how to evaluate these indeterminate limits. Like go ahead and subtract before you just jump into L'Hopital's method. So n to the 1/2 minus n, 1/2 minus 1/3. It's 3 over 6 minus 2 over 6. So this is really 1 over n to the, not 1 over, sorry. That subtracted out to a positive 1/6, right? 1/2 is bigger than 1/3. So you get n to the 1/6 here. So this is not in the denominator. That means that we're just getting infinity here. So again, this diverges, and it has to be by nth term test because the terms are not actually decreasing, they're actually increasing. All right, for the next set, it says approximate the sum of the series by using the first 6 terms. Now I'm going to use a calculator for this to streamline. We haven't really had to, I haven't seen this much like on a non-calc part. So anyway, okay, what are we saying? So we're saying that this sum is approximately equal to S6, the 6th partial sum. So S6 would be equal to, if you plug in 1, I am going to show the terms and then I'll use my calculator. So if you plug in 1, you get -1 squared, so you get 3 over 1. If you plug in 2, you're going to get -1 to the 3rd, so minus 3 over 4. And now I know it's going to alternate, so plus 3 over, what am I plugging in? 3. So 3 over 9 minus 3 over 4 squared is 16 plus 3 over 5 squared minus 3 over 6 squared. Again, I don't want to worry about simplifying. Now, I can either type this in on my screen. It's not that hard to type in those fractions, right? Or you do have summation in your calculator in the math menu. Go toward the bottom. We do have this summation. Most of the new calculators have it. And you would just say x is equal to, this says start at 1. And we just want to go to 6, like add the first 6 terms. And you would type in this expression. So just be careful about it. Now, if you change this to a fraction like this, it will give you the answer as a fraction. So that's fine with me, but just know that. So it's -1 to the x plus 1 times 3. Times 3. I'm not sure if that would have mattered or not. Over x squared gives me this. And let me just double check. What do I get if I do the math just by typing it out? Now this is going to give me a decimal. But remember, you can always math fraction. Oh yeah, we get the same thing. So see, so this is, I'm going to write 2.4325. So we're saying that this sum of the series is approximately equal to 2.4325. Okay, I can do the same thing for the next one. So go ahead, we're saying approximate this with using 6 terms, the 6th partial sum. So I just want to write out what the terms would be. Sometimes you are asked to like write out the first three terms of this and then the nth term or something. So, okay, so if we plug in 1, again, we get negative 1 squared. So the first term is positive, 1 over 2 to the first. The next term will be negative. We're plugging in 2, 2 over 4, plus, plug in 3 over 8, minus 4 over 16, plus 5 over 32, minus 6 over 64. Or I can hop over to my calculator and type in my stuff. So it's in the math menu again. It's option 0 for me. X starts at 1. We're going up to 6. And the expression is negative 1 to the x plus 1 multiplied by x divided by 2 to the x power. This is 3/16. So we're saying the original sum is about equal to 3/16. All right, what about this next section? So I'm going to do this both with a calculator and without, because you might have to do either one for the AP test. So part A says use theorem 9.15, which is our remainder theorem that says the error or the remainder using an nth partial sum is always less than or equal to the first neglected term or the term that you left off of your sum. So determine the number of terms required to approximate the sum with an error less than 0.001. And then B, go ahead and use a graphing utility so we can kind of see the answer I got ahead of time because I left my screenshot up here. But let's see. So I'm going to kind of always write this out. I think the more officially you do your homework, the more likely you are to get free response questions right and not make mistakes doing multiple choice. So I'm writing all of this out. The error between the actual sum and my partial sum is equal to the remainder of that partial sum, and that should be less than or equal to the first neglected term. And we want to keep this less than 0.001, just according to the problem. So let's go with this as if it's non-calculator. So what is a sub n plus 1? In absolute value, so we're ignoring the negative 1 to the n, it's 1 on top, over n plus 1 factorial instead of just n factorial. And we want to keep that less than 1 over 1,000. If I'm not using a calculator, I want to have actual numbers instead of just decimals. Let's go ahead and cross multiply. That means that 1,000 needs to stay less than n plus 1 factorial. You might need to do a little bit of factorial calculation here. There's no way to what's the inverse operation to a factorial? I don't know. I'm just going to go with which one do you know? What's the highest factorial that you know? Hopefully you know 5 factorial is 120. How do you figure out 6 factorial? You do 6 times 120. So that's what? 0, 12, that's 720. So we're not there yet. What's 7 factorial? That's 7 times 720. So 7 times 0, 7 times 2 is 14. Wait. Yeah, sorry. So then I have, hold on, I need to set it up this way. So that's 0, 14. There we go. 49 is, oh, wow. That grew quickly, didn't it? 49 plus 1 is 55,040. I think the reason I paused is because I think I wrote 1,040 on my first key. Did I do that? 1,040. 1,540. Oops, that was silly of me. That should be 5,040. Okay, I'll fix my key. Anyway, the point is 7 factorial should be my answer here. So that means that I know that 1,000 is less than 7 factorial. So that means that n plus 1 needs to equal 7. So n needs to equal 6. All right, so that means that we should be able to use 6 terms. Now, what if I'm allowed to use a calculator? Then I'm not going to bother with all of that math. If I'm allowed to use a calculator, I'm going to type my expression for the n plus 1th term into my calculator. So 1 divided by x plus 1 factorial. Now, factorial is either in the math menu over to probability right here. Or, get rid of that. Or it's alpha, it's one of these up here. I just sort of guess. It's alpha window, I think. Yeah, and it's down there. So however you want to get to that, that's your factorial. And then you go to your table. Now my table is at a weird place. How do I get back without having to scroll all the way back to 0? Second window says table set. So start at 0. Go to your table. So you're looking for when's the first time that this decimal is less than 0.001. So here's 0.0013, so that's too big. This is scientific notation for 0.000198. So that is the first time that you're less than 0.001. So 6 was correct. That's what this screenshot is saying. All right, and then the second part B, was saying, all right, use that graphing utility to approximate the sum of the series. So we're saying that the sum from 0 to infinity of -1 to the n over n factorial is approximately equal to S6. Or S6, you could write that in summation notation. It's the sum from 0 to 6 of -1 to the n over n factorial. So you can do that on your home screen and you get this value. Also note that they tell us what the sum actually is. It's supposed to be 1 over e. That's the exact sum. So here's 1 over e. And I just took a minute to say, like, well, do I get something that's smaller than 0.001 if I subtract my approximation and the actual value? And yeah, I get 0.000176. So this is the error. And we're good. All right, for number 44. Same instructions. So let's treat this like a no calculator problem to begin with. All right, so they're asking me to find the error between the actual sum and a partial sum, which I know is equal to the remainder of that partial sum, which I know is always less than or equal to the n plus 1th term. And I want to keep that less than 0.001. So let's write the expression for the n plus 1th term. So it's in absolute value, so ignore the alternating piece. When you plug n plus 1 into this, it will be 2 times n plus 1 factorial. So that's actually 2n plus 2 factorial. We want to keep that less than 1 over 1,000. So again, I'm going to multiply through. 1,000 needs to be less than whatever 2n plus 2 factorial is. Now, we already did some of the legwork here. We know that 7 factorial is 5,040. So we know that, again, 1,000 will be less than 7 factorial. It's not less than 6 factorial. That's only 720. But that means that 2n plus 2 just needs to equal 7. So solve that for n. Now I'm getting a fraction. I'm getting 2.5. So n needs to be a whole number, right? N is an integer when we're doing summations. So what does that mean? It means round it up, right? So n equals 3. And if you're not sure, like, oh, do I round it up or down? Try it out. I would always err on the side of more terms if I'm trying to get an error. But if I need 2.5 and I round down, then I'm not going to have enough terms to get me less than 1 over 1,000. All right, so let's see. So if we put in 3 into the approximation, because part B was go ahead and approximate this. So we're saying that the sum from 0 to infinity of -1 to the n over 2n factorial is approximately equal to our third partial sum, 0 to 3 of -1 to the n over 2n factorial. I did that in my calculator here. Make sure you start at 0 and note that the one in the previous problem started at 0 as well. So you want to be careful that you're not typing in 1 there. It's whatever the problem dictates. So that is 0.5427 repeating. And then this says that the actual sum is cosine of 1 radian. So I typed in cosine of 1 in my radian mode. I got 0.5403. So yeah, the first 3, it's got 3 decimal place accuracy. So the error here was 0.0 0.0000245, whatever. So yeah, the error is less than 0.001. Again, if you want to use a calculator for that, you would be typing in, let me show you that one more time, sorry. So you would be typing in 1 over the n plus 1. Don't do 1 over 2n. It's 1 over 2x plus 2 factorial, math, probability, factorial, and check your table again. So yeah, our table agrees. This is not less than, this is a little bit more than 0.001. This one, scientific notation, this is less than 0.001. All right, for this one, use the theorem to determine the number of terms required to approximate the sum, and then they don't tell me to find that sum. So same thing we just did. Let's do it without a calc and with a calc. So I am looking at, they're asking me to find the error or the difference of the actual sum and my partial sum. That's the same thing as asking for the remainder of the nth partial sum, which will be less than the n plus 1 term that I left off. And that needs to stay less than 0.001 again. So in absolute value, make this 1 over n plus 1 to the third power instead of 1 over n cubed. We want to keep that less than 1 over 1,000. So now this time I'm not dealing with factorials. I'm looking at what makes n plus 1 cubed bigger than 1,000. So again, I need to, if I'm not doing a calculator, I need to just start with the number that you know the cube of and, just keep multiplying. So like I know that 10 cubed is 1,000, right? I need to be bigger than 1,000. So it's probably just 11 cubed, right? Now, I don't necessarily need to know what 11 cubed is, but we might as well. 11 squared is 121. I think sometimes we forget how to do this stuff. So this one is pretty easy. It's easy to multiply something by 11. Good practice to make sure you remember all of these like elementary math skills. So yeah, 1,000 is less than 1,331. And I got that by saying, well, n plus 1 needs to be 11 because I need to have 11 to the third power. So that means that n should be 10. I need to use 10 terms to get a small enough error that I'm satisfied with. I can do this on my calculator as well. So on my calculator, if that's allowed, I'm not going to bother with all the math. I'm going to say 1 over x plus 1 to the third. I'm going to hop over to my table and scroll in the y column, by the way, so you can see they start rounding these decimals, so see what the actual ones are. When I see 0.001, that's my exact value. That's not what I want. I want something less than that. So yep, it was the 10th term that made that happen. All right, and then our true or false section. So I left my answers up here. Sometimes these are hard to like parcel out what they're saying. So let's look at this. For the alternating series, the sum from 1 to infinity of -1 to the n over n, I just want to make note, the alternating harmonic series. Alternating harmonic series converges. The partial sum, S100, is an overestimate of the sum of the series. So how do we know that? Normally this question in the past has been about concavity, but that's not the case with series. So this is about the error. Let me go back to my calculator. Oh, actually, sorry. Let me go back to my screenshots of my calculator. Depending on the order that I subtracted my approximation and the actual sum, I got a negative value or a positive value. It just kind of depends on what order I'm looking at. So when they're talking about, get that screenshot off, when they're talking about this overestimate, if the 100th partial sum is an overestimate, then it means that the approximation that we got minus the actual sum should be a positive number, right? The error, how far off you are, is positive. If you've taken stats, this is like saying we have a positive residual. We should be on the line, but our approximation is higher than what it should be. Okay, so what does that mean? It means that ignoring the absolute value piece, because we actually want to know the sign, what is R100? What is the remainder of the 100th partial sum? It would be the 101st term. And so if you plug in 101 in for n, you get -1 to the 101, which is -1, over 101. That's a negative remainder. So actually, this is a false statement. The remainder is negative. That means that the 100th partial sum is an underestimate. And again, if you have been in AP Stats, this is like having a negative residual. You're just saying, oh, the line of best fit is where we should be, but my estimate came out underneath. All right, for 78, if Series A and Series B both converge, then their product converges. And at first I was like, oh, this is true, because I'm running through things in my head. Any P series that converges, when you multiply, you would get a P series with an even higher value for P, so that would be true. Geometric, if these are both fractions less than 1, then when you multiply them together, you're going to get a fraction still less than 1, so it's true for those. I wasn't sure about telescoping. I could have investigated that, but then I thought, okay, well, this isn't our alternating series section, so what if they're alternating series? Now, you can come up with some true scenarios for alternating series, but I did find a counterexample. So what if we have an alternating series where the P series has a fraction between 0 and 1. So this would be true, I think, for any fraction between 0 and 1. But it's alternating, so this would converge by alternating series test. And this one would as well. I intentionally made the exponents on the -1 different, but still alternating. If I multiply these two things together, it would just be this. I just multiplied their expressions together. And then remember what you do with your exponents. When you have the same base, you add your exponents. So this would become -1 to the 2n plus 1. And adding these exponents, you would get n to the first. And at first glance, it's like, oh, this is the alternating harmonic series. So that's alternating. But this is where I said, be careful. 2n plus 1 is not actually alternating. So if you have something other than n, or n plus 1 or n minus 1, if you have some other number in there, double check what's happening. 2n plus 1, if you plug in n equals 0, you get -1 to the first. That's negative. If you plug in n equals 1, you get -1 to the third. That's negative. So we're already not alternating. If you plug in 2, -1 to the fifth, that's negative. So think about the expression 2n plus 1. 2n guarantees you have an even number. Plus 1 always makes it odd no matter what. So this is actually, I can simplify this. I don't need the -1 to the 2n plus 1. That's just always going to give me a -1 no matter what. So we're back to having a divergent harmonic series because it's not actually alternating. It's just -1 times the harmonic series. So this one is false as well. Both of those took a lot of thinking. I understand if you did not understand what they were saying. Hopefully after this explanation, it makes a little more sense. But please feel free to come into office hours if we need to talk about these further.